Hello all. Today we will discuss about the Cauchy problem for non-homogeneous wave equations. In the previous lectures, we have already discussed the method of solving the one-dimensional homogeneous wave equation and its corresponding Cauchy problem. And we have already proved that the Cauchy problem for the homogeneous wave equation, a one-dimensional homogeneous wave equation is well paused. Well paused meaning that it has there exists a solution and it is unique and it is stable also. Okay, so now we will discuss about the Cauchy problem for the non-homogeneous wave equation. Its general form is utt minus c square into uxx. In the homogeneous form, the right side function is equal to 0, but here it is equal to um, f of xt, capital F of x comma t, where minus infinity less than x less than infinity and t greater than 0, with the initial conditions u at x0 equal to f of x and ut at x0 equal to g of x, where minus infinity less than x less than infinity. Actually, this problem, for example, models the vibration of a very long string in the presence of an external force, capital F. So, the capital F represents the external force actually. And as in the homogeneous case, the functions small f and g are the given functions that represents the shape. F represents the shape and g represents the vertical velocity of the string at the time t equal to 0. So g represents the vertical velocity of the string at a time t equal to 0. Okay. Now we will we will prove that this non-homogeneous equation always admits at most one solution. Okay, the that can be proved from the uniqueness of the homogeneous problem, or we can say that the uniqueness of the homogeneous problem implies the uniqueness for the non-homogeneous problem. Implies the uniqueness for the non-homogeneous problem. Now the proposition is the Cauchy problem given by equation 1, the Cauchy problem, that is utt minus c square into uxx equal to f of xt, and where minus infinity less than x less than infinity t greater than 0, u at x0 equal to f of x, ut at x0 equal to g of x, for minus infinity less than x less than infinity. That is equation number 1, admits at most one solution. Admits at most one solution. So we need to prove that if the Cauchy problem, the non-homogeneous Cauchy problem has a solution, or if there exists a solution, then at most it admits at most one solution. Okay, that we need to prove. For proving the proposition, first we assume that there are two solutions, u1 and u2, for the given Cauchy problem. So let this be equation number, the Cauchy problem be equation number 1. Then assume that u1 and u2 are the solutions of problem 1, then we need to prove that if the equation has a solution, we assumed that let u1 and u2 be any two solutions of the problem 1. Then we need to prove that uh, u1 is equal to u2. We need to prove that u1 equal to u2. Okay. Assume that let u is equal to let u equal to u1 minus u2. So if you since u1 and u2 are the two solutions of the non-homogeneous equation 1, we have it should satisfy the equations both for u1 and u2. Then u1 minus u2 will be a solution of the corresponding homogeneous equation. Okay, that is since u1 and u2 are solutions of the non-homogeneous Cauchy problem 1, we have u1 at t minus c square into u1 of xx is equal to f of xt with the given initial conditions. And since u2 is a solution, we have u2 of t minus c square into u2 at xx is equal to f of xt with the same initial conditions for u2. Then taking the difference of these two equations of the two equations, we have um, u1 minus u2 of t minus c square we can take outside u1 minus u2 of xx, isn't it? Dou square by dou x square of u1 minus u2, which is equal to f of xt minus f of xt, that will be 0. Now we have taken u1 minus u2 as u itself, that is we have utt minus c square into uxx is equal to 0 with the same initial conditions. That means u is a solution. That means u equal to u1 minus u2 is a solution of the corresponding homogeneous problem. Is a solution of the homogeneous problem utt minus c square into uxx equal to 0, where minus infinity less than x less than infinity, t greater than 0, u at x0 equal to f of x. Sorry, u at x0 will be their difference, isn't it? Because u1 and u2 both satisfy the conditions that u1 at x0 is f of x and u2 at x0 is equal to f of x. So u1 minus u2 at x0 will be f of x minus f of x, that is equal to 0. Similarly for the function for the second condition u1 of t u1 of t u1 t at a x0, sorry, dou by dou t of u1 at x0 is given as is equal to g of x, and similarly the same for u2, then for their difference it will be equal to 0. So the initial conditions for the homogeneous equation for which u is a solution will be u at x0 equal to 0 and ut at x0 is equal to 0, where minus infinity less than x less than infinity. Now look at the equation, the Cauchy problem. Look at the homogeneous Cauchy problem, which is given by the equation number 2. Now, equation number 2 is a Now 2 is a uh, Cauchy problem for the one-dimensional wave equation. And we have already proved that we have a theorem which states that the Cauchy problem for the one-dimensional wave equation is well paused. Okay, and one more thing, also when we consider u as or another solution, consider the function v at xt is equal to 0. Also, v at xt is equal to 0. If we substitute v in the equation number 2, then it also then it is 0. The identically equal to 0. The 0 function will also satisfy this the homogeneous Cauchy problem given by equation number 2, isn't it? Since v is equal to, which is identically equal to 0, and then its second derivatives are also 0 and first derivatives are also 0, so that means it satisfies the equation 2. That means v of xt equal to 0 is a solution of the is also a solution of the homogeneous problem given by 2. So we have obtained two solutions. U equal to u1 minus u2 is a solution, and v equal to 0 is also a solution. But the equation 2 has one and only one solution. Since it is well paused, this we have already proved. So we have both the equations will be, both the solutions will be equal, therefore u1 minus u2 equal to 0, which implies u1 equal to u2. So if the non-homogeneous Cauchy problem for the one-dimensional wave equation has a solution, then it must be unique, that is given by at most one solution. If it has a solution, then it must be unique. So first we have proved that if u1 and u2 are two solutions, if there existed solution, let u1 and u2 be any two solutions, and then we proved that both are equal, both are the same by considering its difference. U is equal to u1 minus u2. Since u1 and u2 are the two solutions of equation 1, its difference will be a solution of the homogeneous equation that is given by this equation number 2. So, since the homogeneous equation, Cauchy problem for the homogeneous equation is well paused, and also 0 function is also a solution of equation 2, we can have u1 is equal to u2. Okay.